Hello, welcome back. We have been looking at how to find the magnetic field of a moving charge. And then we also looked at the magnetic field due to a current in a short segment of wire. And then we looked at the magnetic field due to a current in an infinitely long section of wire. And now what we're going to start to look at is the magnetic field due to a current loop. And then we'll look at how a current loop is actually a magnetic dipole, just like a permanent magnet. So let's start by looking. First, let's review what we found already. We found that the magnetic field of a long straight wire carrying current I, capital I, at distance little r from the wire is equal to mu naught over 2 pi times I over little r, where little r is the distance from the wire. And that's the magnitude. Now to find the direction of the magnetic field, we will take our handy right hand, take our thumb, point it in the direction of the current, and then our fingers will curl around in the direction of the magnetic field, which will be tangent circles around our current carrying wire. Now what we want to do is to find the magnetic field of a current loop, which is a circular loop of wire with radius capital R that carries current capital I. And we want to find the magnetic field at a distance Z, which is on the axis of the loop. So let's first talk about what is a current loop. So first we look here and we see that we have a practical current loop. So in reality, if we're going to have a current loop, that means that it must be connected to something. So it must have a place where it's connected, where you can get a current generated that's coming in from one end. And then it, of course, will have to connect out on the other side as well. But we are going to consider this to be just an ideal current loop where we have a continuous wire with a current going around our continuous wire. And this current, we said, has a radius capital R. And what we're interested in finding is the magnetic field at some point Z that is on the axis. So we're looking on the axis of our loop. So our loop is going to be on the Z-axis. We're going to put our loop on the Z-axis, and right in the center of it, we're going to go all the way out and find some point Z, and that's where we want to find our magnetic field. So let's work on setting this up. So we want to find the magnetic field of a current loop at a distance Z on the axis of the loop. So here we have our current loop that we just saw. And of course it has radius capital R, so radius capital R, and current capital I. So here's our current capital I going around our loop, our current loop. And it is on right through the center of it. This is the Z-axis. This is the Z-axis right through the center. And we want to find the magnetic field at some point Z out here. And the first thing that we want to do to find the magnetic field is we want to find a segment. We'll pick a segment that'll make our lives easier. So let's pick this segment right up here at the top of our loop. This is segment I, and it has a length delta S. That's the length of our segment. It's some length delta S. And so the length is delta S, and the current at this point in our loop is going directly along the x-axis. So we see that the current is pointing directly along the x-axis. So delta S sub I will be the displacement vector for our current that is pointing directly along the x-axis. Now, in that case, what we see is that delta S, and we also draw the vector for the distance between our segment I and our point over here, point Z. And so that distance is little r. So that distance is little r. And the vector right here, r hat, that means that it is the unit vector. So it has a magnitude of 1, and it's pointing in the direction of r. Now we notice that delta S and r hat are completely perpendicular to each other. So they are 90 degrees to each other. So r hat is, so delta S is right there along the x-axis, and r hat is pointing down. It's pointing down. So it is still 90 degrees from delta S, but it has a downward slope to it. And that angle that it is down, that it is from the y-axis, from our radius r, is phi. So that's the angle that it's pointing down right here. And so if we then want to find out what the magnetic field is at point Z due to segment I, we of course want to find the direction of that magnetic field. And then we can use the Biot-Savart law to tell us the magnitude of the magnetic field due to segment I. And then we can sum up over all the different little segments around our loop to get the total magnetic field at point Z. So first, let's figure out what would be the direction of the magnetic field due just to segment I. Well, we know that the Biot-Savart law tells us that the direction is going to be delta S cross r hat. So the direction of this, find delta S cross r hat. We're going to take our fingers, our right-hand fingers, point them in the direction of delta S, and then curl them around in the direction of r hat. And we see that our thumb will be pointing up and to the right. So it'll be pointing up and to the right. So the magnitude, so the direction of the magnetic field due to segment I out at point Z will be up and to the right. Now let's also look at segment J down here. So segment J is exactly 180 degrees opposite of segment I. So segment J, in this case, the current is going directly, if we draw a tangent line to the direction the current is going at segment J, right at the bottom of our loop, it is going perfectly parallel to the x-axis in the opposite direction. And so if we draw our vector delta S sub j, it is going to be pointing directly parallel to the x-axis, but now in the opposite direction. And so if we want to find the magnetic field due to segment J, which also has a distance r from point Z, then it will have an r hat also in this direction. And if we take our delta S in this case and cross it with r hat, in this case, we will have our thumb pointing down and to the right. So this time it'll be down and to the right. So that's what the magnetic field will be due to segment J. So let's draw both of those. So here is the magnetic field due to segment I. So it's pointing up and to the right. And the magnetic field due to segment J is pointing down and to the right. So here's segment I pointing up and to the right, and segment J pointing down and to the right. Now, if I split these into their components, I see that for both the B sub I and for both B sub J, they have this will be B sub I sub Y that is pointing straight up, and B sub J sub Y, that the components of these two are equal and opposite, so they will cancel each other. Then the components in the Z direction for BIZ, and also we'll have BJZ. So BIZ will add to BJZ. And so those components will add in the Z direction. So the only components, and if we note, and we'll notice that if we do any other segments, let's do the segments over here where the current would be pointing directly in the Y direction, the positive Y direction here and the negative Y direction over here. So for these two, we would notice that they're, in this case, they will only have an x component, but those x components will cancel. And the only thing that will add will be their z component. So for any segment along our loop, the only component that we will keep is the z component. So this z component, we can see, if we draw our triangle here, our z component in this case, with this is angle phi, the z component will be the adjacent over the hypotenuse being b sub I. So we see that cosine of phi will be equal to the adjacent, so that'll be bi z over bi. And so that tells us that the piece that we're looking at, the important part that we want to find here, this bi sub z, is going to be equal to bi, the magnitude of the magnetic field due to the I segment, times cosine of phi. Now, to find what the magnitude of bi is, we need to use the Biot-Savart law. So here's our Biot-Savart law, and that tells us that the magnitude of the magnetic field, will be equal to mu naught over 4 pi times I delta S cross r hat over r squared. And we see that we found that delta S cross r hat, we found the direction of that. Well, if we get the magnitude of that, that's going to be equal to the magnitude of delta S times the magnitude of r hat, which it's just a unit vector, so that's just 1. That clear, that's just a 1 there, times sine of the angle between them. And we see that the angle between them, again, they're perpendicular to each other, so the angle between them is 90 degrees. So sine of 90 degrees is just 1. So this will be equal to just delta S. So this piece right here is just going to be equal to delta S. So the magnitude of bi is going to be mu naught over 4 pi I over r squared. And we know that what we want is bi sub z, where bi, which was equal to bi times cosine of phi. So if we take this piece right here and we put it in for b sub I, we see that bi sub z is going to be mu naught over 4 pi I delta S over r squared times cosine phi. So let's start from what we found right here, this expression for the magnetic field due to segment I. So let's start with that right here. We know that we had mu naught over 4 pi I delta S over r squared times cosine phi. Well, r squared, little r right here, we see this is a right triangle, and we know a squared plus b squared equals c squared, where r here is the hypotenuse. So r will be equal to the square root of z squared. This side right here is length z, and the other side is length capital R. So little r squared will just be z squared plus capital R squared. So I can put that in right here. And I see that I now have mu naught I cos phi. I've taken my delta S and put it on the side. Just move those around. Over 4 pi times z squared plus capital R squared. Now what we need to think about is this cosine phi. Well, cosine phi, we see that phi right here, this angle right here, is going to be the complement of this angle right here. And if this angle right here is the same thing, this is 90 degrees between these here and here, this is 90 degrees. And so cosine phi is going to be 90 degrees minus this little angle right here, this little zeta. And so that means that this angle up here is angle phi, which we already saw earlier too. And so in that case, we can say if this angle is angle phi, we know that cosine theta is going to be adjacent over hypotenuse. So cosine phi is equal to the adjacent, which will be capital R, over the hypotenuse, which will be little r. And we know that little r is r over z squared plus r squared to the 1/2. So if I take this expression for the cosine of phi and I put it in here, I can then rewrite this as mu naught I times capital R, put capital R in there, over 4 pi. And instead of having z squared plus r squared by itself, that was to the 1, I multiplied that by to the 1/2, so I get to the 3/2. We add those together. 1 plus 1/2 will be 3/2 times delta S. So this is now our full expression in terms of z and r and s, delta S, for the component, for the magnetic field due to segment little I. So now what I want to do is sum over all the little segments. So sum over all these little segments, split my loop into all these little segments and sum over all my little delta S's. These all will be little delta S's. So I want to now sum over all the little delta S's. And I see that when I take the sum of b sub I sub z, I'm going to take this expression and I'm going to sum over all of them over all the i's. So that's a total, the total pieces that I've split this up into. And I see that the only thing that actually is changing, our capital I doesn't change, our capital R doesn't change. Z is the same for everything. Capital R is the same for everything. So the only thing that's changing between each one, we're going to add up all those little pieces of delta S. So when I sum over all of my little pieces of delta S, I see that I'm going to add up all the pieces of delta S. And so the sum of delta S is just the circumference of my loop. And the circumference of my loop, I know, is 2 pi capital R. So I can then put this in for the sum of my delta S. And I see that in this case, the magnetic field due to the entire loop is equal to mu naught IR over 4 pi z squared plus r squared all to the 3/2 power times 2 pi capital R. Well, I can simplify this because I can cancel my r's, my pi's here, and I can cancel 2 and 4, and I'll have a, I'll just divide the 2 out of both of those, and I have a 2 down here. And then I can combine my capital R's, so that'll end up being r squared. Let me write this up. Here's r squared. And so when I rewrite this, I end up with mu naught over 2 times capital I r squared over z squared plus r squared all to the 3/2. And that is the magnetic field of a current loop. So we see that the magnetic field of a current loop with radius r that carries current I is, and that's on axis. This is the on axis magnetic field of a current loop, is mu naught over 2 times I r squared over z squared plus r squared all to the 3/2. And this is, again, on axis. This is for the on axis. If we get off axis, it gets a lot more complicated, and we'd have to evaluate it numerically. We couldn't just evaluate it with a simple integral. Now, another thing that's interesting is that frequently, we don't have just one loop, but rather a coil of loops. So it would look something like this, where we would have a coil of loops. And we will say that we have, in this case, let's say we have a total of n loops. So we add those up, we have a total of n loops. So the magnetic field at the center, so this is just right at the center. So again, it's only right at the center, where z equals 0. So if z equals 0, that means that this term would go to 0. And we have n terms, so a total of n. So we're just going to multiply this whole expression by n. So we multiply it by n. If z goes to 0, then r squared times 3/2 would just go to r cubed. And we have an r squared in the top. So this r cubed will cancel with this r squared in the top, and we'll just have an r on the bottom. And so we see that for a coil in the center, the magnetic field in the center of a coil is going to be mu naught over 2 n times I over capital R. Let's look a little more closely at what's going on with the magnetic field of our current loop. We found the magnitude for for our current loop. But now we also need to figure out the direction and the shape of this magnetic field for a current due to a current loop. So in order to do that, we take our current loop and we see if we have a current that is going through our loop, and we've cut the loop here in half. So right, the screen is just cutting the loop in half. And we see at the bottom right here, we see an X. That means that the current is going in down here, right? We're seeing the tail feathers of our arrow. So the current is going in at the bottom and it is coming out at the top. We're seeing the point of the arrow coming out here, pointed at you, coming out at the top. And so if I take my fingers and I take my right hand, my trusty right hand, and I put my fingers in at the bottom and have them curl out at the top, my thumb will then point in the direction of the magnetic field. So I see that in this case, if my fingers go in at the bottom and out at the top, my thumb will point from left to right, right in the center of my magnetic field. And that will show me that the magnetic field is going from left to right. I can also take my thumb and point it in the direction of my current. So it will be going in. And in that case, my fingers, my loop will be going in. So my fingers will then curl towards the center. When they curl towards the center, I want to see them at the center of my loop. So any place around my loop, I have to be able to have my thumb go around my loop. And then my fingers will always be going in the direction to the right in this case. So that's another way to do it. Now, what you saw as I did that is that as my thumb is going around, this drawing looks like it might be two-dimensional, but in fact, it's three-dimensional. That means that everywhere we have the magnetic field going out one side and curling around it back and coming back in the other side. So everywhere around our loop, we have this magnetic field that is going through it and coming back around throughout the whole loop. This figure over here is now looking back at our loop to the right. So we're now looking back, seeing it from the right. And so if we see it from the right, we see right in the center, we see these dots, which are telling us that our magnetic field is coming out towards us. We see the arrows coming towards us. And on the outside, that we see the X's, which tell us that it's going into the screen there. So it's going into the screen for you guys, into the screen there, where we see the X's. And so we can take our fingers and have them go around our current. And so if they're going around our current in this direction, our magnetic field will be coming out of the screen. Will be coming out of the screen. Let's see if I can do that for you. I don't think I can. It'll be coming out of the screen at you. All right. Now, the fact that this is three-dimensional and that it's going in all directions, we can see that, again, we can use these iron filings. And if we put iron filings and then we have a current loop, once we have the current going through that loop, these iron filings will line up and we'll see the pattern of our magnetic field, which will be going through our loop. And we see that it'll be going in circles around our loop here, which I didn't do a great job drawing there. There we go. Where it's going through the loop and coming back into the loop on the other side. Now, when the magnetic field leaves on one side and comes in on the other side, what we know is that that means that we have a magnetic dipole. So it's leaving on one side and coming in on the other side. And the side that it leaves on, that's the north side. And the side that it comes in on, the magnetic field lines come to, is the south pole side. So we can say that a current loop is in fact a magnetic dipole, where the side where the magnetic field is going out of the loop is the north pole side, and the side that the magnetic field lines are coming back in through the loop is the south pole. This is just like a permanent magnet, where the north pole is where the magnetic field lines go out, and they go out and come back around to the south pole. So whether it's a current loop or a permanent magnet, the magnetic field emerges from the North Pole, always emerges from the North Pole. Now, the magnetic dipole moment of a current loop that is enclosing an area A. So let's say this is area A, loop area A right here. And if the loop, no matter what shape the loop is, if it is enclosing area A and it has a current I, we define our magnetic dipole moment, which we use as mu, another mu, I know, but it's not the same as mu naught. This is now our magnetic dipole moment, and that will be equal to A times I. It's the area times the current, and it will point from the South Pole to the North Pole, like we just saw. If we take our fingers and follow them around the loop, we see that it will point in the direction that will point in the direction of our magnetic dipole moment, which points in the same direction as our magnetic field that is going through the loop. So the magnetic dipole moment is going to be perpendicular to the loop in the direction of the right-hand rule, where the magnitude of mu is going to be A times I. So using the fact that the magnetic dipole moment is the area times the current from the South Pole to the North Pole, we see that if it's area times current, that the magnitude, that the units for area we know are meters squared. The units for current we know are amps. And so the SI units for the magnetic dipole moment are meters squared times amps, or in this case, amps times meters squared. Now, if we want to find the on-axis, this is only for on-axis, the on-axis field. So that would be some point on axis, for on the axis. Some point on the axis. The on-axis field of a magnetic dipole, which is what we just found here, is going to be mu naught over 4 pi times 2 mu, where mu in this case is going to be the magnetic dipole moment, over z cubed. This will be our distance z, and that will give us our on-axis. That'll be the magnetic dipole moment that we'll be able to use to give us our magnetic field due to our magnetic dipole that we have from our current loop for an on-axis magnetic field. So we see that just by having an electric current going through a loop, we are able to generate something that gives us a magnetic field that is not just a magnetic field, it's actually a magnetic dipole, just like a magnet, just like a permanent magnet.